Hello and welcome. In this video, we're going to be talking about uniform circular motion and specifically centripetal force, and then working some example problems with centripetal acceleration and centripetal force. So if you haven't seen my previous video on uniform circular motion, where I'm talking about centripetal acceleration and centripetal velocity, I highly recommend that you go back and watch those first, because I'm going to be talking about some of those concepts again in this video so that you can understand how centripetal acceleration and centripetal force tie together. So let's go on and get started. Uniform circular motion dealing with centripetal force. So what exactly is centripetal force? Well, again, we have to go back and look at the kinematics. And according to Newton's second law, net force always equals mass times acceleration. So an object that's accelerating has to have some type of net force acting on it. And as we talked about in the previous video, when I have an object in circular motion, there is an acceleration towards the center of that circle. That is centripetal acceleration, the center-seeking acceleration. Well, based on kinematics, whatever direction the acceleration is facing, that is the same direction that the force is facing. So if I've got acceleration centripetal acting towards the center of the circle, then I have a force also acting towards the center of the circle. That force that's associated with centripetal acceleration, that is centripetal force, or the center-seeking force. We symbolize this as F sub c. So here's the idea. If I didn't have that net force being applied to something in circular motion, then I would apply an initial force, and we would actually see that object just fly off in a straight line, because it's going to obey Newton's first law. Okay? So we know there's got to be some center-seeking or centripetal force. Now, I want to talk to you very quickly about a huge misconception in physics, and that is this idea, of centrifugal force. Centrifugal force does not exist. And I know some of you will go, wait, now, I've taken something on the end of a string and I've twirled it around and I've felt this outwards force. So if you're telling me that there is this center-seeking force, then based on Newton's law, action-reaction, if there's a force inward, there has to be some force outwards. That is centrifugal force. And I'm telling you, no. Centrifugal force does not exist. But here's where the misconception comes in. It comes in because, indeed, you do feel a pull on your hand from the string. But that's just Newton's third law of action-reaction, where you feel a force outwards due to an inward force that you are applying to that string to keep the object in that circular motion. So let's kind of zoom in on this and think and talk and show how this is actually working. Okay? So I've got this stopper on a string again. Right now it's just hanging there. If I want to put this into vertical circular motion, notice the first thing that happens with my hand. Y'all see it? I had to jerk it upwards to get it to start moving. So I'm applying a force upwards, or in this case, towards what's going to eventually be the center of the circular motion. And as it moves upwards, I jerk back downward. That pulls it back down. And what you would find if you could take this motion and slow it down is that when this object is here, my hand is actually pulling again opposite from it. I'm exerting a tension force in this string, or a force inwards, that's causing it to stay in circular motion. So when we've got in circular motion, you tell my hand is moving a little bit. Okay? And if I exaggerate that, what we'd find is that at every moment I'm pulling in a direction opposite from where the stopper actually is. So I'm exerting an inwards force myself to keep this in circular motion. When I apply an inward force, the string exerts an outward force of tension, and that's the force that you're feeling on your hand. You're not feeling centrifugal force because, again, there's no such thing as centrifugal force. All right, but let's just assume for a moment that there were this thing called centrifugal force. Well, if there was actually centrifugal force, which again, there's not, if I've got this circular motion and there's a force always exerting outwards, this imaginary centrifugal force, when I let go of it, that force would cause it to move off in a straight line. Okay? That's not what we see. We don't see it move in a straight line directly outwards from its circular path. What we see is it flying off in a straight line that is tangential to the circular path. So the fact that if I have this in circular motion and I let go of the string, that it's going to move off in a straight line that is tangential and not outwards in a straight line means there's no outward force acting on it. What we have is a tension force in that string that is counteracting the pull of my hand and the force that my hand is exerting to keep it in circular motion. So no such thing centrifugal force. And I know some of you might be thinking, but wait, Mr. Johnson, what about when I'm in a car? I'm not tied to the center of that car. Well, that's when it's your inertia trying to push you outward of that path. So if I'm in my car and I'm moving straight and I start to go around a curve, my inertia wants to keep me moving straight. That's what inertia does. It's a resistance to the change in motion. So as I'm moving straight and my car starts going into that curve, my body wants to continue moving straight. Well, what that does is it pushes my body up against the door, or if I'm driving, pushes me towards the passenger. But that, again, is not a centrifugal force. That is simply your inertia trying to keep you moving in a straight line. Turns out that straight line is directly outwards from that circular motion. Okay, so again, we don't have centrifugal force, whether that it is an object tied to a string or it's you sitting freely in a car going around a curve. It's either going to be your inertia that's pushing you out in that straight line, or it's going to be an action-reaction force between the force of your hand, keeping it in circular motion, and a tension force in the string. Okay? So hopefully that all makes sense. But the key point is this. There's no such thing as centrifugal force. There is only centripetal force, because that's the only acceleration that we have within circular motion, is a centripetal acceleration. Okay? So moving on to kind of summarize these key points. First off, when we look at force centripetal, F sub c, because it's along the same vector component as our centripetal acceleration, it is also going to always be perpendicular to the velocity vector anywhere along that circular path. So as you can see in this, force centripetal, perpendicular to velocity, and therefore directed towards the center of the circle or center of circular motion anywhere along that circular path. Secondly, the last bullet point from the previous slide is, again, this idea, getting rid of centrifugal force. I've got a force exerted by my hand on that string to keep the ball in circular motion, and therefore I get a force on the ball exerted by the string. This is your action-reaction pair. Okay? So centrifugal force does not actually exist, and we actually do refer to this as an apparent force. Okay? So don't be surprised if you see centrifugal force in your physics textbooks, but your textbook should be very clear that it does not actually exist, that it's an apparent force. So if ever you're working problems in physics and it asks you to explain an outward motion of something in circular motion, please don't ever answer it as being centrifugal force, because that's going to be an incorrect answer. You're going to get it wrong. Okay? You done goofed if you say centrifugal force. Okay? Again, that pull that you're experiencing is simply the reaction force to the tension in the string, and that's what obeys Newton's third law. Okay? So I feel like I've kind of beat that to death. So moving onwards, back to kinematics. How do we actually calculate this centripetal force? Well, we start with our basic equation that net force is going to be equal to mass times acceleration. Well, if our acceleration is centripetal, or radial acceleration, radial, any of those terms, then what we get is that net force centripetal equals mass times that acceleration radial, or radial acceleration. And since radial acceleration equals v squared per r, as we talked about in the previous video, we can substitute in and get that the net force centripetal equals mass times velocity squared, all divided by the radius. So this is the most basic two equations that you've got for centripetal force. Okay? Centripetal force is mass times acceleration centripetal, or force centripetal equals mv squared per r. But there's an additional formula. Because we've got this expanded equation of mass times velocity squared per r, we can substitute in the equation for circular velocity, which again is 2 pi r per t, or how long it takes to go through one revolution, or the circumference, so 2 pi r squared. We can plug these in together, we can substitute in, and initially we get this equation that says force centripetal equals mass times 2 pi r per t, all squared, and then divided by r, which simplifies down to net force centripetal equals mass times 4 pi squared times r, all divided by the period squared. So with those equations in our arsenal now, we're going to go on and take a look at how to work some of these problems. So the first problem here, a 0.150 kilogram ball at the end of a string is revolving uniformly, and that key term uniformly means uniform circular motion, in a horizontal circle of 0.6 meters. The ball makes 2 revolutions in a second. So as always, the first thing that we're going to want to do is identify what we're given. So I've got a mass in kilograms, I have a radius in terms of meters, and then the ball makes 2 revolutions in a second. So that's 2 revolutions per second. And since this has units of revolutions per second, that is my frequency. So the first question is, what is its centripetal acceleration? Well, if you recall, centripetal acceleration, or a sub r, equals v squared per r, but I don't have the velocity just given to us. But we do know that velocity equals 2 pi r per t. Well, I've got the radius, but I don't have the period. But I know that the period equals 1 over frequency. So with these equations, I can now rewrite this to where I'm going to end up having the idea that acceleration radial will end up equaling 2 pi r per 1 over frequency. And then that 2 pi r would need to be squared because over here velocity is squared. So now when I substitute in all of these values, what I get is 2 pi times my radius of 0.600 meters. And that is going to then be divided by 1 over frequency. So if my frequency is 2, then that is going to be a value of 0.5. And that, and this is what I forgot in here, sorry. So this is square, and I still have to divide by that radius. I knew something looked a little bit off. So my radius is 0.6, and then again all of this gets squared. So when I plug that into the calculator, what I'm going to find is a centripetal acceleration of 94.75, and it would come out as meters per second squared. Okay. Now, that's doing it all at once. If you would prefer to first convert that frequency over to a period, plug it into this velocity equation, solve for the velocity, and then plug into your acceleration radial equation, you'll get the exact same thing, because obviously, as you can tell, whenever I work through this, I kind of forgot part of the equation. And then as I started looking, recognized that the 2 pi r per 1 over frequency all squared, that is simply velocity. So I'd taken care of my velocity squared, and then I went back and added in that divided by radius to make sure that the equation all worked correctly. But now that I've got my acceleration, now I can go about finding what that centripetal force is. And again, force centripetal is going to be mass times acceleration radial. So therefore, if you haven't learned that symbol, it's an important little symbol. The 3 dots as a triangle means therefore. Therefore, force centripetal is going to equal the mass of 0.150 kilograms all times that velocity, the acceleration centripetal of 94.75 meters per second squared. And when you do that math, you can go on and pause and work that, and then you can unpause to be able to check your answer with my work. I end up getting a value of 14.2, and kilogram meters per second squared is the same thing as newtons. So here is my centripetal acceleration, and then my centripetal force for that ball revolving in uniform circular motion. So that's an acceleration problem and then a force problem. So let's take a look at another one. The moon's nearly circular orbit around Earth has a radius of about, so it tells me this value is my radius. It has a period of 27.3 days. That I'm going to end up having to convert to seconds. And then determine the acceleration of the moon towards the Earth. Okay, so first thing I want to do is take this period of 27.3 days, and I want to convert that over to seconds. So the first thing I'm going to end up doing is recognizing that there are 24 hours per every 1 day. This will allow the units of days to cancel out and tell me how many hours that would be. I'm then going to convert those hours onto minutes you can do, or what I'm going to do is recognize that there are 3,600 seconds for every 1 hour, because it'd be 60 times 60. And in doing so, hours will cancel, leaving me with seconds. And I calculate a value of 2.36 times 10 to the 6th seconds. So that's the period. Okay. So now determining the acceleration. Well, acceleration, centripetal or radial acceleration, again, is going to end up being v squared per r. I don't just have a velocity, so I'm also going to have to use the equation that v equals 2 pi r per t. And this time I'll work it in 2 separate problems to show you how that's done. So first off, velocity would be 2 pi times that radius of 3.84 times 10 to the 8th meters, all divided by this period of 2.36 times 10 to the 6th seconds. And that gives me a velocity of 1022.5 meters per second, approximately. And then I can take that velocity and substitute it into my acceleration equation. So 1022.5 meters per second, all divided by that radius of 3.84 times 10 to the 8th meters. And we don't need to forget to square that velocity. And when we do that, we should end up with the value around 2.72 times 10 to the negative third, and that will give me units of meters per second squared. Okay. Again, don't forget, at any time that I'm working these problems, please feel free to pause the video, work ahead. Once you've got your answer, then you can unpause and watch me work through it and verify that you got the right thing. Okay. By the way, I did do a little bit different of rounding in this. So if you didn't come up with exactly 1022.5, don't worry. Okay. As long as you got something close to that. Okay. I think in my papers that I've got in front of me, I was using some slightly different values than what's in this problem. And I'm looking at my paper. My paper shows 1022.3, not 0.5 meters per second. So just understand, I do use a little bit different of values. I'm using a little bit more accurate of values than what they just give me in this problem. But anyway, hopefully you understand the process that I'm taking. So next question, this is just a purely conceptual problem. And it asks, in the game of tetherball, or when the game of tetherball is played with the ball tied to a pole string, when the ball is struck, it whirls around that pole as shown in the figure. In what direction is the acceleration of the ball? And then what causes that acceleration? Now, if you're taking AP chemistry, or not AP chemistry, AP physics, sorry, a lot of times they're going to give you these diagrams, and the diagrams give you all the information that you really need. And if I look at this, what I notice first off is that they're showing a force of tension in that string. And because it's set at some angle, what that means is I'm going to have a force of tension along the X and a force of tension along the Y. That's going to be important. So if this is in circular motion, what we know about circular motion is that there's always going to be an acceleration towards the center of that circle or that circular path. So I've got my acceleration centripetal pointing towards the pole. And if you look in this diagram, what you'll notice is that the acceleration centripetal is in the same direction as the force of tension in the X. So to this question, what direction is the acceleration of the ball? Towards the center of the circular path. What is providing that acceleration? That's going to end up being the force of tension in the X that's causing that particular acceleration. So those are the problems that I have for you for this unit. And as always, hopefully everything made sense. If not, feel free to leave me questions in the comments and I'll get back to you as soon as possible. Also, if you have ideas for future videos, you can leave those in the comments. And then lastly, don't forget to subscribe to this channel so you get updates whenever I upload new videos. Thanks. Take care.